Welcome to Yung Tuition. Let's talk about wave equation today. We encounter various forms of wave every day. When I'm talking, I generate a sound, which is a mechanical wave. Our ears receive the sound all the time in the form of wave. And when we make a phone call and we rely on electromagnetic wave, so wave is everywhere. How do we describe a wave in a graph and more importantly, in an equation? Let's talk about this issue. Before that, let's draw a coordinate. This is our y-axis. This is our x-axis. In x-axis, in this case, represents the position or the coordinate in space, whereas the y-axis represents certain quantity, which is oscillating or time-dependent. If we imagine there is a source at origin, and it is oscillating all the time, then we can describe this periodic motion by introducing a concept called amplitude, A, and the lower part would be negative A. So you can imagine that if there's a oscillating locating at the origin, it could be a real particle, or it could be simply an electrical field or magnetic field oscillating. In this case, the wave is generated because wave can propagate, travel in space at a certain speed. If we denote the speed as a v, so that is a wave speed. Let's just consider one-dimensional wave here. So if the wave speed is v, then we can actually draw a picture of this wave according to, based on the oscillation. So if we just wait, here are these are three basic concepts here. Wave is a speed, is wave speed. It's constant, given a medium. But in the case of electromagnetic wave, the wave speed is always a constant. Second, we're talking about the amplitude. A is the amplitude. That would be max displacement from the equilibrium position. Other idea is a period. It's called a period. And the reciprocal of period is called the frequency. Frequency equal to 1/t is called the frequency. In addition, I would like to introduce another frequency called angular frequency, denoted by Greek letter omega. Omega is simply multiply the frequency by 2 pi. Okay, these are the basic quantity to be used to build the wave equation. Let's just return to this diagram. If we're waiting for exactly one period, the oscillator will go, during that time, the oscillator will go up and back, continue to the lowest position, and return. So that would be the variation in this red dot. Now, on the other hand, we know that wave will travel at a constant velocity. So therefore, we can calculate how far this wave has traveled, whether it is visible or invisible wave. Suppose that during that exactly one period, then the wave have traveled here. Okay. Now the distance can be measured by using the velocity multiply the time, or we can write this position as velocity multiply the time if we're waiting for exactly one period. Okay. So this length we give the name is called the lambda. So this is called the lambda. Additional concept here is wavelength. Okay. So if you visualize this wave, in this case, because it's transverse wave, so we can visualize this wave by drawing this curve, which you will find very familiar if you recall your mathematics in high school. So that would be the graph at this particular moment. So we're waiting for exactly one period. And we took a picture, took the photo. That would be the wave you would be able to see, or you be able to measure. So this is obviously the sine wave, the sine function, right? So can we do it again? This is a high, make this more accurate. That should be a sine wave. Okay. And this length is called lambda. So graphically, we can see that this from the origin to this point will be called the one wavelength. Okay. Now, mathematically, how do we describe this curve? Well, we can immediately come up with this formula. So y x as function of x and the time t. But at this moment, can we call this moment is t equal to 0? Okay. This is a t equal to 0. In this case, we can write the wave equation as a multiply the sine theta. Okay. Theta is angle. Okay. In our case, we are interested to find the coordinate or the position. How do we do that? We just scaling. We do some scaling so that we can get this more useful or explicit equation for this sine wave, that is 2 pi divided by lambda multiply x. And these two notation are equivalent because we know that the period for sine theta is 2 pi. And in this case, when x equal to lambda, the period, the theta or this, you are looking for this cancelled. So that is a justification how to describe this wave at this t equal to 0 moment. Next, we just assume that waves still propagate in space. So next moment, you will see the wave is shift or displaced or moved toward the right. And the displacement, can we denote this displacement by, say, the delta x? Okay. So delta x in this case can be worked out. So in this case, the delta x here can be simply written as the wave speed multiply a time. Okay, by the way, we started counting time. This is t equal to 0, and this would be t equal to t, just non-zero. So in this case, according to our knowledge, we can simply translate this function. We know that after time interval t, and the dashed graph, let's finish this complete graph. Okay. So we can simply using our knowledge of translation in mathematics. So that would be x minus delta x. Okay. Okay, let's focus on this phase term. So we have 2 pi lambda x minus x. X delta x, as we know, is equal to velocity wave speed multiply the time t. Okay. What we do next is, can we just expand? We just put the lambda into the equation, 2 pi. We got x over lambda minus velocity over lambda multiply the t. Okay. So from this formula, by the way, from this formula, we can, because we have velocity multiply period equal to lambda. So therefore, velocity will equal to t lambda divided by t, or equal to lambda multiply frequency. So in this case, therefore, v over lambda will equal to exactly frequency. Okay. So this term will be frequency. So next, what we do is we we expand the 2 pi. We can put the 2 pi back to the each term. We got 2 pi divided by lambda and multiply x. The next term will be 2 pi frequency multiply the time t. So what is a 2 pi frequency? What is a 2 pi f? There's another formula. I will highlight this formula. So can we use, so this is the formula we're going to use. So these are basic formula for describe wave. So that is a basic formula here. Okay. So last, we can rewrite this 2 pi f as omega, right? So that this term will equal to omega. So in this way, we can obtain the wave equation for a sine wave, the simplest regular wave. So in this way, we can find the equation sine, that is a bracket, 2 pi over lambda multiply x, take away the omega t. Okay, this is the wave equation we're looking for. Of course, in the real case, that the wave cannot be as simple as just the sine wave, but it doesn't matter because according to Fourier transform, any wave can be, any oscillation can be considered as the linear combination of the sine wave. So any function, so any wave xt can be written as the different sine wave yi xt and I from 1 to infinity. So that is why we have found the mathematical expression for the sine wave. By using Fourier transform, we can describe any wave in any forms. Let's stop here. Have a nice day and goodbye.